Hi guys, we are studying in this lecture series Complex Analysis 1. That is the first module of your syllabus, in which up to the last lecture I have finished your first topic, first chapter, analytic function. And now from today I am going to start your second topic of this first module, that is complex integration. Because as in our introductory lecture I discussed, I told you in complex analysis actually we have to discuss all the calculus properties of the complex function, in which first differentiation of complex function that is converted into the analytic function I have discussed and I have finished in the last lecture, and from today I will going to start complex integration. Complex integration, if we have z is a function, complex function, z equal to u iv, and you know that z is x plus iv as a complex number, then we take an integral I as integral c fz dz, or you can say as in closed integral c fz dz. This is a complex integral where C is a curve in the z plane, or you can say complex plane. This is complex plane. Origin x-axis and it means real axis, y-axis means imaginary axis. Then C is a curve. If C is a closed curve, here C is a closed curve, means initial and final point are coinciding, then we take this type of notation for integration. Both are the complex integral. This integral is also known as contour integral. Another name, contour integral, means if we are taking a complex integral along a closed curve like circle, rectangle, square, triangle, then it will be a contour integration. This will be contour integration. This is the path. Naturally, from this decision, you can see that the complex integral is a type of definite integral because it is along the path. So we can open this complex integral in complex in notation, because you know that fz is equal to u plus iv. Dz means dx plus I dy, because you know that z equal to x plus iy. If you open this and take real and imaginary part, u dx is the real part, I square, then minus v dy is imaginary part, then I times v dx and plus u dy. You can open this in Cartesian form, then integration with respect to x, with respect to y, with respect to x, with respect to simply. This is the complex integration. Means complex integration is a type of definite integral, and that can, any function can be integrated along given path by the property of, by the formula of definite integral. So this is the basic introduction of complex integration. So for that, we take an example by which you more clear that example. If we have an example, evaluate integral 0 to 2i mod z bar square dz along number 1 path is the real axis to 2 and real axis to 2, and then vertically to point 2 plus I. This is the first part, and second part, the line y equal to x equal to 2. This is the numerical example, numerical sum, by which you can understand what is the basic concept of complex integral, right? Here, this is our real axis and imaginary axis, and this is 0, 0 means origin, 2 plus I means a point 2 comma 1, or you can say that 2 plus I. So this is line. First path, first solution here, we have the function mod z bar square, then z bar means x minus I bar conjugate of the complex function. Open this is x square plus I square means minus 1 minus y square minus I times 2xy. This is the expansion of this function. Now, in first case, path is real axis, integral 0 to 2 plus I z bar square dz. Path is real axis up to 2 means x equal to 2, x bar 0 to x equal to 2. And then vertically up to 2 plus I, that means y equal to 0 to y equal to 2. Path is x equal to 2 line. And from here y is 0, so dy is 0. From here x equal to 2, so dx equal to 0, x is constant. Then this integral break into two parts, x equal to 0 to 2 for first part, z bar for z bar y is 0, that is x square, dz here dz equal to dx, here dz equal to I dy, because you know z equal to x plus I. So in first case z bar is equal to only x square because y is 0, and dz equal to dx plus vertically means along the line x equal to 2 from y equal to 0 to 2. Here the z bar is, because x equal to 2, z bar is 4 minus y square minus 4y I times, or dz is I times dy. Now on this path, if we converting them into the Cartesian form, so here we see that this complex integral simply transformed into a definite integral. First with respect to x, second with respect to y. Now solve these two, calculate this further. This is first case, s square means s cubed by 3, upper limit, lower limit. In second case, 4 integration of 1 is y, integration of y square is y cubed by 3 minus I 4. Integration of y is y square by 2, limit y equal to 0 to 2. This is after substituting limit 8 by 3. This is after substituting limit, this is 8. This is minus 8 by 3. This is minus I times 8, and at the y equal to 0 or in the vanishing, that is equal to 0. To cancel out, that is this. Now calculate this again. Further calculate this. This is 8 by 3 and into I. Calculate this, that is 8 by 3. This is 16 by 3 minus I square into I. I square is plus I. That is 8 by 3 plus 8 plus I 16 by 3. This is 32 by 3 plus I times 16 by 3. That is 16 by 3. That is 2 plus I. This is the answer of the first part. Value of integral along real axis up to 2, then vertically. Now, in second part, this is the path. Line y equal to x by 2. Y equal to x by 2. Then y equal to x, then dy equal to 1 by 2 dx, and this implies that dz equal to dx plus I by 2 dx, that is 1 plus I by 2 dx, means integral dz is converted into dx. And this is path, if we take z plane, then like that, this is the path y equal to x by 2. And integral x equal to 0 to z equal to 0 to 2 plus I, 0 means that is 0, 0, that is 2, 1. So from here, when x equal to 0, then y is 0. From this relation, because we have given y equal to x by 2, when x equal to 2, then y equal to 1. Then this integral becomes integral x equal to, then this equal to x equal to 0 to 2, this is the limit, and this expression we have opened this x square, because we have z bar square, open this, that is x square minus y square minus 4 times I xy. If z bar we open 2 times I x by, right? This is the whole square open. Then on this y equal to x, then x square, y square means x square minus 4 minus 2i times x, y means x by 2, or dz means 1 plus I by 2 dx. Then here we are transferring entire integral with respect to x. So here we are taking a limit of x. Calculate this, x equal to 0 to 2. This is 3x square by 4. This is I x square. This is 1 I plus by 2 dx. Now this is simply a definite integral with respect to x between limit 0 to 2. So you can solve easily it. That is I equal to, integrate this, 3 by 4 integration of x square is s cube by 3 minus I times s cube by 3, x equal to 0 to 2, and 1 plus I by 2 is constant value, which is already multiplied. Now substitute the value, 3 is cancel out, that is 8 by 4 minus I 8 by 3, that is 1 plus I by 2. This is 2 minus I 8 by 3, 1 plus I by 2. Now multiplying these, open this complex multiplication, that is simply 2 minus I 8 by 3 plus I minus plus 4 by 3, that is 10 by 3 and minus I 8 by 3, and this, if we take common this, this is minus 3, means I times minus 5 by 3. If we take 5 by 3 as a common, then we get 1 minus I. This is your answer of the second part of the question, and that is the basic concept of the complex integration. Means complex integration, simply if we calculate this, if we have to integrate any complex function, then there will be given a path. So first take the path, draw this on z plane, and by this path convert the two variable concept into single variable, and then that will be transformed, that will be reduced into a simple definite integral. Solve this, you get the result. Now in this chapter there are number of theorems, number of lemmas. By using those, we can solve the given definite integral. First, I am taking here theorem, that is Cauchy's integral theorem. Cauchy's integral theorem. This is a very useful and very important theorem, but its proof is beyond your syllabus. So statement is the only important, that is, statement is if fz is an analytic function, if fz is an analytic function on the and inside a closed curve C. If function is analytic, if we are taking a closed curve C like that, if function is analytic on the C, means on the boundary of C and inside the C, then Cauchy's integral theorem states that integral C fz dz is equal to 0. This is the statement of Cauchy's integral theorem. If a function is analytic in a closed domain and also on the boundary of that domain, then if we take integral of that function along C, then this is equal to 0. This is the theorem, and proof is beyond this. It can be proved but not part of syllabus, so we are leaving that proof. And second thing, actually there is a number of types of the curve, closed curve, arcs, cards, and there are also type of a you can say multiply connected region. Multiply connected origin, like that. If we connected two circles, this is C1, this is C2, and then this concentric circles. So this is a multiple connected region. Then there is a statement of Cauchy's integral theorem for this type of this, that is also very useful in some proof. Cauchy's integral theorem for multiply connected region. This statement is also converted for such type of region, and that is very important to prove some other theorems, some other formulae in this chapter. What is this? If fz is analytic in a multiply connected region R, by two concentric circles C1 and C2, then this theorem states that integral C1 fz dz equal to integral of fz along C2. Means value of integral along both the path, both the circles, closed circles, will be same, must be same. So this is another statement of Cauchy's integral theorem if we are taking here multiply connected region. How is possible? Logically you can see that if we have C1, C2 and this is the region between two circles, and we take a cut M, we take cut M1 and we plan this if region is R, so you can see that fz is analytic in R. So by Cauchy's theorem we can take integral of fz along R must be 0. Just I stated this theorem. If any function is analytic in a closed domain, in a closed curve C, then integral along that curve of given function is vanishing. Now, what is R? By figure, if we see that R, if we start C1, then R is first curve. If we take this clockwise C1, after C1, the second, if you complete this circle, then if you take this cut, then this is NM, C1, then NM, then again from here, this is NM, and then C2, right? But C2 is just reverse form. We take minus C2 and then MN. Actually, this is if we take two concentric circles C1, C2, and we take a cross cut and open this to this type of figure. So this R is means that is C1 plus NM minus C2 plus Mn Fz equal to dz. If you open this by the property of that integral, we get four integrals: C1 Fz dz plus integral along Nm Fz dz minus integral C2 Fz dz plus integral along arc Mn Fz dz, and right hand side is 0. So you see that integral number second and integral number 4 both are the same integral but sign opposite. So value will be equal but sign opposite. So these two will be cancelled out and you transfer this, then we get our required result, that is integral along C1 equal to the integral along C2. That is the another statement of Cauchy's integral theorem for multiply connected region. That was the first theorem of this chapter. And now, before starting another theorems, another formula, first I will take a numerical sum on Cauchy's theorem, by which you can see what a important statement of this theorem. What is this? How is the application of this theorem? So first we take an example here. Find integral over C 3z square plus 7z plus 1 upon z plus 1 dz, where C is the circle mod z equal to half. This is the numerical problem, and this value of integration, we see that in solution of this differential, this integral is very simple after using Cauchy's integral theorem. Here in complex notation, always you have to remember is z minus z1 equal to r. That denote equation of circuit. Always this, where z1 is center and r is radius of this circuit. So here this is the figure. This is, if you draw this on z plane, this is x-axis, this is y-axis, then this is the circle, center origin and radius 1 by 2, right? And here fz is 3z square plus 7z plus 1 upon z plus 1. We see that if this function fz is not analytic only at z equal to minus 1, means that is only singular point in this. And here we see that z equal to minus 1 is not lying inside C, because minus 1 is here, radius is 1 by 2. So minus 1 is lying, not lying inside C, means minus 1 is existing outside this circle. So therefore, by Cauchy's theorem, we can see that integral C 3z square plus 7z plus 1 upon z plus 1 dz is equal to 0. Directly you can write this without any calculation, because here given function is analytic in C. Because given function is only not analytic at z minus 1, at z minus 1 point is lying outside the circle. So we can say that fz is analytic inside the C. So by Cauchy's theorem, directly we can write the value of this integral is equal to 0. This is the example, numerical example of Cauchy's integral theorem. And now, next thing, that is the Morar's theorem. Morar's theorem. Or you can see that that is another name, that is converse of Cauchy's theorem. Converse of Cauchy's theorem, only statement is a part of our syllabus, not proof. So what is converse? Because in Cauchy's integral theorem, the statement was if a function is analytic on and inside a closed curve C, then integral of given function along C is equal to 0. So here the statement, if fz is a continuous function on and inside a closed curve C, and integral C fz dz equal to 0. Then fz is analytic on and inside C. This is the converse of Cauchy's theorem and is called Morar's theorem. Morar's theorem. Right? If function is continuous on a closed curve C or inside a closed curve C, and its integral along C is equal to 0, then function fz is analytic and inside C. Means our function we have to check the analyticity of any function. So we can also check by the using of integration. If integration is 0 and function is continuous, then by Morar's theorem, means converse of the Cauchy integral theorem, we can say that function is analytic on the inside C. This is simply converse part of the Cauchy's integral theorem. Now, come on, next formula, next theorem that is very important, that is Cauchy's integral formula. Cauchy's integral formula. This is another theorem, another formula, and its proof is also part of course. What is the formula? If fz is an analytic function with an closed curve C and z equal to a is any point inside C. If fz is an analytic function within a closed curve C and z equal to a is any point inside C, then f of a, value of function at point A, can be expressed 1 upon 2 pi I integral C fz upon z minus a dz. This is the Cauchy's integral formula. A function is analytic and this is a point inside C. If we have a curve C and z equal to a is a point, then function is analytic then we can express value of function at that point in form of this integral, and this is known as Cauchy's integral formula. This is the statement of this theorem, is formula. Its proof is also part of this, and in this lecture now I am finishing this two statement. In this lecture, first I will prove this Cauchy's integral formula, then also some advancement and extension of this theorem, this formula, that is the Cauchy's integral formula of the derivative of function. By this formula, we can also find the derivative of function, means f dash a, f double dash a, up to the f and a. And then I will take some numerical example on this theorem. Okay, thank you.